Intermittent fasting, IF, as you all may know by now, is a term used to describe various eating patterns in which no or very few calories are consumed for time periods that can range from 12 hours to several days on a recurring basis. A recent scientific study on intermittent fasting and its health benefits focuses on the physiological responses of major organ systems, including the musculoskeletal system, to the onset of the metabolic switch triggered by intermittent fasting. This intermittent fasting-induced metabolic shift can be described as the point of negative energy balance at which liver glycogen stores are depleted and fatty acids are mobilized, typically beyond 12 hours after cessation of food intake. The findings from this study suggest that the metabolic switch from glucose to fatty acid-derived ketones represents an evolutionarily conserved trigger point that shifts metabolism from lipid cholesterol synthesis and fat storage to mobilization of fat through fatty acid oxidation and fatty acid-derived ketones, which serve to preserve muscle mass and function. Thus, it has been concluded that intermittent fasting regimens that induce the metabolic switch have the potential to improve body composition in overweight individuals. Moreover, intermittent fasting regimens also induce the coordinated activation of signaling pathways that optimize physiological function, enhance performance, and slow aging and disease processes. First, let's look at the physiological responses of the different organ systems in a human body that are triggered by intermittent fasting in detail. Studies of laboratory animals and human subjects have shown that intermittent fasting can improve cognition, learning, and memory. The underlying mechanisms may involve neurotropic factors, stimulation of mitochondrial biogenesis and autophagy, and the formation of new synapses. Intermittent fasting also increases the resistance of neurons to stress and suppresses neuroinflammation. In humans and rodents, intermittent fasting results in decreased levels of circulating insulin and leptin, elevated ketone levels, and reduced levels of pro-inflammatory cytokines and markers of oxidative stress. Robust beneficial effects of intermittent fasting on the cardiovascular system have been documented and include reduced blood pressure, reduced resting heart rate, increased heart rate variability, improved cardiovascular stress adaptation, and resistance of cardiac muscle to damage. One key mechanism responsible for many of these beneficial effects appears to be flipping the metabolic switch. This switch represents a shift from lipid synthesis and fat storage to mobilization of fat in the form of free fatty acids and fatty acid-derived ketones. The metabolic switch typically occurs in the third phase of fasting, when glycogen stores and hepatocytes are depleted and accelerated adipose tissue lipolysis produces increased fatty acids and glycerol. The metabolic switch usually occurs between 12 and 36 hours after food consumption is stopped, depending on the liver glycogen content at the beginning of the fast, and on the amount of the individual's energy expenditure or exercise during the fast. The lipids in the adipocytes are then metabolized to free fatty acids, which are released into the blood. Simultaneously, other cell types may also begin generating ketones, with astrocytes in the brain being one notable example. Free fatty acids are transported into hepatocytes, where they are metabolized by beta oxidation to produce the ketones beta-hydroxybutyric and acetoacetate, which may in turn induce mitochondrial biogenesis. Growing body of research indicates ketones are the preferred fuel of both the brain and the body. Therefore, it is hypothesized that once the metabolic switch occurs, both the tolerability and sustainability of intermittent fasting regimens are greatly increased.